Good morning. So, our new series or our first series is about writing an OS in Rust. This blog is old as it was dated on 2018, but it now supports a Rust 2014 version. So it's a new overview of the blog written by Philip. It is inspired from many series I saw on YouTube, but they were old, maybe 2 to 3 years old. So we will be reviewing the new latest version of the blog. And I'm also creating this blog because I'm not an computer guy. So it will keep me motivated as I am a creator guy. So let's get started. The first chapter is about writing a freestanding Rust binary. The first step in creating our own operating system kernel is to create a Rust executable that does not link the standard library. That's explainable. This makes it possible to run Rust code on bare metal without an underlying operating system. Yeah, if it's an executable, you don't need a library, right? This blog is openly developed on GitHub. Yeah. So we have all this. The introduction, the introduction to the blog. To write an operating system kernel, we need code that does not depend on any operating system features. This means that we can't use threads, files, heap, memory, the network, random numbers, standard output, or any other features requiring OS abstractions or having specific hardware, which makes sense since we are trying to write our own operating system and our own drivers. This means that we can't use most of the Rust standard library, but there are a lot of Rust features that we can use. For example, with Rust, we can use iterators, closures, pattern matching, option and result, string formatting, and of course the ownership systems. These features make it possible to write a kernel in a very expressive, high-level way without worrying about undefined behavior or memory safety. So we can use Rust for our help, and we will get all this. That's nice. Of course, we get memory safety as well. In order to create an OS kernel in Rust, we need to create an executable that can be run without an underlying operating system. Such an executable is often called a freestanding or bare metal executable. So that explains it. This post describes the necessary steps to create a freestanding Rust binary and explains why the steps are needed. If you are just interested in a minimal example, you can jump directly to the summary. We won't. Disabling the standard library. By default, all Rust crates link the standard library. Yep, we do. Which depends on the operating system for features such as threads, files, or networking. It also depends on the C standard library libc, which closely interacts with OS services. Since our plan is to write an operating system, we can't use any OS dependent libraries. So we have to disable the automatic inclusion of the standard library through the no standard attribute. Okay, so now it supports 2024 cargo build. Uh, I named the project bloggers, but of course you can change it. The bin flag specifies that we want to create an executable binary in contrast to a library. Yeah, an executable binary is understandable now. It is standalone. It will have a main function instead of a lib.rs. And the addition, it specifies the 2024 edition. Let's do it. Now our blog base is created. Contains a cargo to terminal. We have we have cargo.toml and src. The cargo.toml contains the crate configuration. For example, the crate name. Yeah, we know that. We have a name. We have to. The VS Code up and running. Sorry for that. Here we have a main rotaris with us. The no standard attribute. Right now, create implicitly links in the standard library. We don't need to do that though. Let's try to disable this by adding the new standard attribute. The no standard attribute. If you add this no standard attribute, uh, what it does, it unlinks the standard library. Okay, you build it now. Let's build it. So to build it. We get some warnings. Create level attribute should be an inner attribute. We get these warnings. We do not get the similar warnings to this. So, I don't know. Oh, we didn't unlink it. Sorry for that. We didn't unlink it. No sender attribute. Now we just run it again. Now it shows us panics. And here is you cannot find the macro in this. So yeah, println is with this standard library, I guess. The reason for this error is that println macro is a part of standard library, which we no longer include. So we can no longer print things. This makes sense since println writes to standard output, which is a special file descriptor provided by the operating system. Okay. So println comes with or bundles with the standard library and we can't use it. So let's just clean it as they did in this. So nice. Now the compiler is missing a panic handler function and a language item. We need to build it again. Let's build it. It says it's a panic handler. So we just copy it from here. We need a panic handler language item. What is a language item? We didn't get the same error. EH personality. Yeah, we didn't get the error. Let's just go ahead. The panic handler attribute defines the function that the compiler should invoke when a panic occurs. Ah, the standard library provides its own panic handler function, but in no standard environment, no STD environment. We need to define it ourselves. So we need to write it ourselves. So use code. Thank you for that. The standard library provides its own okay. The panic info parameter contains the file and the line where the panic happened, the option panic message. And this function is called on panic. And we need to create a function for panic as well. What is this? Uh, Copilot is helping us a lot. Thanks for that. The panic info parameter contains the file and line where the panic happened. The optional panic message, the function should never return, so it is marked as a diverging function. So it is a diverging function, okay. By turning the never type, that the exclamation mark, there is not much we can do with the function for now. So we just loop independently, indefinitely. Okay. So the panic parameter contains the file and lines where the panic happened and it is passed as. But this function should never return as in case of panic, as we do not have the panic options we get with the standard library, so we don't return it. The EH personality language item. We didn't get this error though. The language items are special functions and type that are required internally by the compiler. Okay. For example, the copy trait is a language item that tells the compiler which types have copy semantics. When we look at the implementation, what is the implementation? Okay, so we don't have this lang copy. Okay, this is an example. Like the state is a language item. Okay, so we see it has a special yes that defines it as a language item. While providing custom implementations of language item, it is possible. It should only be done as a last resort. The reason is that language items are highly unstable implementation details and not highly implementation details, and not even type check. So the compiler doesn't even check if a function has the right argument types. Fortunately, there is more stable ways to fix the above language item error. And I don't know if we should do that. The EH personality language item marks a function that is used for implementing stack unwinding. Stack unwinding is like emptying the stack when something happens. By default, Rust uses unwinding to run the destructor. All live stack variables in case of a panic. Okay. This ensures that all used memory is freed and allows the parent thread to catch the panic and continue execution. Unwinding, however, is a complicated process and requires some OS specific libraries, example lib unwind on Linux or structured exception handling on Windows. So we don't want to use it for our operating system. So stack unwinding is tough, and if we create it, it's like complicated. So we don't create it. So we disable it. Yeah. So there are other use cases as well for which unwinding is undesirable. So Rust provides an option to abort unwinding instead. So unwinding the stuff, so we are disabling it. That's the whole summary of that. There are other use cases as well for which unwinding is undesirable. So Rust provides an option to abort unwinding instead. This disables the generation of unwinding symbol information and thus considerably reduces binary size. There are multiple places where we can disable unwinding. The easiest way is to add the following steps to our cargo.tom. We can do these. So just go to cargo.tom. We need to add these for developer profiles. Profile.dev. Need to add panic equals to abort. And for the what is this profile? Profile needs. I guess it is for the production profile. Panic equals to abort. Oops, sorry. So this disables the unwinding, the stack unwinding. This sets the panic strategy to abort for both the dev profile used for the cargo build and the release profile used for the. So our stack unwinding is called in case of panic. So in case of panic, we just abort the panic. Now the EH personality language item should not be required. Just do it. There is one error. FMain requires the standard library. Panic info. Yeah. What did we do? Okay, this was an intentional. Let's run it again. So now we have to use slash says we have to use into the bypass the Rust generated entry point. Let's see what it suggests us. The start attribute. One might think the main function is the first function called when you run a program. So for your information, I'm also learning the operating system with the U. I have no experience how an OS runs or how an OS works. I'm an electronics major, by the way. One might think that the main function is the first function called when you run a program. However, most languages have a runtime system, which is responsible for things such as garbage collection, In Java, I've read Java. Software words like Go routines in Go. This runtime needs to be called before main since it needs to initialize itself. In a typical Rust binary that links the standard library, execution starts in a C runtime library called C runtime 0, CRT0, which, which sets up the environment for a C application. This includes creating a stack, placing the arguments in the right register. The C runtime then invokes the entry point of the Rust runtimes, which is marked by the start language item. Rust only has a very minimal runtime, which takes care of some small things such as setting up stack overflow guards or like backtrace on a panic. The runtime then finally calls the main function. Okay, our freestanding executable does not have access to Rust runtime and CRT0. So we need to define our own entry point. Oh, so our Rust run bare metal does not have the Rust runtime and the underlying C runtime. So we need to overwrite CRT0 and entry point directly. Okay. So how do we override the entry point? To tell the Rust compiler that we do not want to use the normal entry point chain, we need to add the oh, that's what it says. So we need to add the entry. Let's just add it. No, oh, thank you. Let we add the no man attribute. You might notice that we remove the main. Oh, this they remove the main function. They remove the main function. You might notice that we remove the main function. This reason is that a main function does not make sense without an underlying runtime. It calls it. Instead, we are now overwriting the operating system entry point with our own start function, which is unsafe, no mangle. I don't know what it does. I just add the start function at the top. It's the OG way to do it. So which we don't do this. We write unsafe. It is unsafe. We write no mangle. Oops, sorry for that. And we write pub extern. Why do we write it though? We should disable copilot. Disturbing my learning. Start. And we loop it. Okay. Disable copilot. Code completion. Okay. By using the unsafe no mangle, we disable the name mangling to ensure that the Rust compiler really outputs a function with the name start. Okay, so no mangling is used to ensure that the Rust compiler really output a function with the name start without using the attribute. The compiler would generate some cryptic symbol to give every function a unique name. So the Rust compiler would give the function a cryptic name if we don't use the no mangle attribute over here. Okay. The attribute is required because we need to tell the name of the entry point function to the linker in the next step. So we would create a linker. We also have to mark the function as extern C to tell the compiler that it should use the C calling convention for this function instead of the unspecified Rust calling convention. This is the reason for naming the function start is that this is the default entry point name for those systems. Okay, so we will be using the C calling convention for this function and not the Rust way. So that's why we are using the default entry point name, which is the start. Yeah, this is the but we just learned this. Right? This is a diverging function that doesn't return anything. It is not allowed to ever return. Oh, it is not allowed to. In a way, it is not allowed to return, and yeah. So it is not. It doesn't return anything, but it is not even allowed to return something. This is required because the entry point is not called by any function, but invoked directly by the operating system or the bootloader. So instead of returning, the entry point should invoke the exit system call of the operating system. In our case, shutting down the machine could be a reasonable action since there is nothing left to do it. We're free setting binary returns. For now, we will fulfill the requirement by looping endlessly. When we call cargo build now, we get an uglier link error. So just call it. Okay. So yeah, linking with CC fail, we get a link error. Yep. What is a link error? The linker is a program that combines the generated code into an executable. Since the executable format differs between Linux, Windows, and macOS, each system has its own linker that throws a different error. The fundamental cause of the error is the same. The default configuration of the linker assumes that our program depends on the C runtime, which it does not. To solve the error, we need to tell the linker that it should not include the C runtime. We can do this either by passing a certain set of arguments to the linker or by building for a bare metal target. What we are doing? We are building for a bare metal target. By default, Rust tries to build an executable that is able to run in our current system environment. For example, if you're using Windows on x86-64, Rust tries to build an .exe Windows executable that uses x86. This environment is called your host system. Okay, the Windows is our host system, or x86 is our host system. To describe different environments, Rust uses a string called target triple. Can you see the target triple for your host system by running Rust C version verbose? Okay, C Rust C version verbose and recognize Rust C version verbose. I guess I'm getting this error because I'm running it on my Ubuntu, which is like a virtual environment. So just run it on this Rust C version. Oh, version verbose. I'm getting some unrecognized option E. I don't know how to do that. So this is what I should have got, but I'm not getting it. Above output is for an x86-64 Linux system. We see that the host triple is x86-64 unknown Linux GNU, which includes the CPU architecture x86. Windows and both use the same. Oh, it's the CPU architecture, not the Windows one. The vendor unknown operating system Linux and the ABI GNU. GNU, we write it, we don't write it, GNU, right? By compiling for a host triple, the Rust compiler in the linker assumes that there is an underlying operating system such as Linux that uses the C runtime by default, which causes the linker error. So to avoid these linker errors, we can compile for a different environment with no underlying operating system. An example of such a bare metal is Thumb V7M target triple, which describes an embedded ARM system. ARM like a phone, an Android phone. Uh, I've heard of ARM laptops. The details are not important. I don't know about the ARM architecture, even though okay, let's come. The details are not important. All that matter is that the target triple has no underlying operating system. It is indicated by the none in the target triple. To be able to compile for this target, we need to add it in the rest of. Okay, so we are telling the compiler that we have no underlying OS, so let's just add it to add it in the rest of. I'm just editing this. Right? Let's copy this. I hate it. Rest up. Try it. at thumb v 7 em none. What's that? EABIHF. This downloads a copy of the standard and the core library for the system. Now we can build our freestanding executable for this target. It's downloading. So we will have the Rust std for this particular target, and we will not need to use any of the operating system, underlying operating system. By passing a target argument, we cross-compile our executable for a bare metal target system. Since the target system has no operating system, the linker does not try to link. But internet is there. Yes. This is the approach that I just forgot what I was reading. By passing a target argument, we cross-compile our executable for a bare metal target system. What does that mean? We cross-compile our executable for a bare metal target system. Okay, yeah, we cross-compile it. Since the target system has no operating system, the linker does not try to link the C runtime and our build succeed without sending error. So it fixes everything. It's done. It's done. It's installing. I guess it's done. This is the approach that we will use for the building our OS kernel. Instead of thumb, we will use what? We'll use a custom target that describes a x86 bare metal environment. The detail will be explained in the game. The linker arguments. Instead of compiling for a bare metal system, it is possible to resolve the linker errors by passing a certain set of arguments to the linker. This isn't the approach that we will use for our kernel. Therefore, the section is optional and only provided for the completeness. Like we should do this. I guess we should do this. We'll get all of the learning from the code block, or should we not do this? Let's do this faithfully, I guess. In this section, we will discuss the linker errors that occurs on Linux, Windows, and how do you do. Let me just become. Ah, we can read this. This is the end of our program, right? Yeah, let's do this. Let's use it. This we are not so far. Is the recording up and going? Yeah, recording is up. It's just 28 minutes in. Let's do this. So the following core arguments. Let's start it. Instead of compiling for a bare metal, it is possible to resolve the linker errors by passing a certain set of arguments to the linker. But we just did the for the bare metal, right? We don't need to do for the link argument, so you can just skip it. So there were two ways to I just get to know now. So we have two ways by passing arguments to linker or by using the bare metal target. They're using the bare metal target as the suggested. The summary. For the summary of this blog or this video is a minimal freestanding Rust binary just look like this. It doesn't link. Yeah, let's just go here. So the no standard, it doesn't link the Rust standard library. The no main, it disables all the Rust level entry points, like calling the main function, using the CRT0 and the Rust runtime. We use the core panic info, and we have the panic function over here. The panic function is used when the executable is on panic. The unsafe no mangle attribute is used to disable the mangling. Like, for example, the mangle is, we learned it over here, right? Where is the mangle? How about not this? This. Yep, here is it. So we use the no mangle for disabling the name mangling to ensure that the Rust compiler really outputs a function with the name start without the attributes. Like if you don't use the no mangle over here, uh, the Rust would just create a some cryptic symbol like this for a function. It would not name it the name start, which will cause error because our runtime now calls a start function. And if we don't have a start function, it causes panic or a linker error, something like that. So we need to create new mangle so that the function is get by the name start and it can now execute our main.rs as the C runtime requires it. That's why we use an external C. So it uses the C-based function calling and it doesn't follow the arbitrary Rust way of calling functions or creating functions. This function is independent since the linker tools for a function. Since the linker looks for a function named start by default. Okay. Yep. Our cargo.tom. This is the author. This is the versions. It disables the stack unwinding. It is for the developer version and it is for the release version. To build this binary, we need to compile for a bare metal target such as this one. So we use this example. This is the target. So what is the target? We just learned about it. This is a system with no underlying operating system. It fixes our linker errors. These are the other ways to fix it by using linker passing arguments. So now, note this is just a minimum example of reasoning. The binary expects various things. For example, the stack is initialized when the start function is called. So for any real use case of such a binary, more steps are required. Making the Rust analyzer happy. Let's just go on to this. What is this? I don't know. This is a short read. That's why I started the video because I could now focus on the blog. Making Rust analyzer happy. The Rust Analyzer project is a great way to get code completions and go to definition support and manage the feature of Rust code in your editor. So this is something else. This is not from according to. So this helps our project. The Rust Analyzer, if you're using the check on say feature of Rust Analyzer inbuilt by default, it might report an error found duplicate. Whereas the Rust Analyzer invokes cargo check all targets by default, which also tries to build the binary in test and benchmark. Two meanings of target. The all target flag is a complete unrelated target argument. These are two all different meanings. Target is in cargo, the car target flag. This is where the compilation target that should be passed to the RustC compiler. This should be set to the target triple. I don't get it. By default, however, Rust will choose check all the package targets by default when check on save is enabled. This is the reason that Rusty reports the Bob Lang item error and we do not see the cargo check. When the cargo check, we see that I error too. Okay, just search the cargo check. Here the cargo check all targets. All oops, all targets. We get white. We need to see this error. So we then so now should create something like this for us to see. Found duplicate lang item panic implementation. So it found something. Yep, we got the same error. We got the same error.
The first node tells us that the panic language item is already defined in the STDK, which is the dependency of the test crate. The test crate is automatically included when building a create in the test mode. This does not make sense for our no-std kernel. It is an std attribute we put in the main.rs, as there is no way to support the standard library on the bare metal. So this error is not relevant to our project and we can safely ignore it. Okay, we are using the panic, so we can safely ignore it because we do not have an underlying panic function in our standard library because we do not have a standard library. The proper way to avoid this error is to specify in our cargo.toml that our binary does not support building in test and bench modes. You can do that by adding a bin section to our cargo.toml to configure the builds of our binary. You can have a bin, have a bin. ठीक है, ऐसे ही. We need to add it in our bin, right? Sorry for that. I'm get it. You create something else for this? I've never created the bin. Just doing what it says. Bloggers. I haven't done about bin or something like this. You have Copilot for that though. Bench and benches also. So this is just, I know this is for querying the not using the test and bench modes. Okay. Double brackets around bin are not a mistake. This is how the TOML format defines keys that can appear multiple times. Since a crate can have multiple binaries, the bin section can appear multiple times in cargo.toml as well. This is also for the reason for the mandatory name field, which needs to match the name of the binary so that the cargo knows which settings should be applied to which binary. Okay, okay, now I get it. Bin runs again and again, so it is required to use a name field so it knows for which binary it should run. We instruct cargo to not build our. I get it. Now cargo check all should not throw any errors. Mine does though. Sorry. Sorry. No, no it doesn't. It's running in that in 0 seconds. What's next? So now we have completed this blog, and what's next? The next post explains the steps needed for turning our freestanding binary into a minimal operating system kernel. We'll be building a kernel, right? Yeah. This includes creating a custom target, combining our executable with a bootloader, and learning how to print something to the screen. Yeah, so we are done. We have created a Rust binary, a freestanding Rust binary. Rust binary is nothing but an executable that is bare metal. It doesn't have something like an underlying OS to run it. It's it's bare metal. It doesn't use this under library, and we have our own start function. So that's all for today, or should I read more? I should read more. I will just come tomorrow for this. Each episode one day.